Welcome back. If you keep coming back, it means you are getting what? Your time's worth, right? It's a vote of confidence and a vote of thanks from us. Okay, now we looked at this differentiation of exponential functions. We've done the one part where we said, you know what, we ended up saying the differential with respect to x of a to the power of x is simply a to the x by the limit as the small change in x tends to 0 of a minus what? I made a mistake. I spoke and I wrote different. I spoke something and I wrote something different. I previously made this a power as well. I made it a dx minus 1 as if dx minus 1 was in its entirety was a power. But quite frankly, it was a slip of the pen. It was supposed to be on the ground. It wasn't supposed to be an exponent. I hope you picked that up, and I hope if you did, that would mean you were awake. That means there was no disaster, there was no shock. But right now, if you didn't, it means you probably got lost. Hopefully, you will find yourself if you go back and if you revisit that section and you do that part right. And then that was obviously over that small little change in x. It's very important to say things correctly and write them correctly, but sometimes the mind and the pen and the hand get disjointed between the thinking and trying to explain and whatever is happening around you. So it's a little bit of yeah, I hope you know what I'm talking about. Now, in any event, for when x tends to 0, you remember at 0, 1, we have one function which has at 0.01 the gradient is 1. Therefore, this part being that gradient being 1, that function has a derivative identical to it, and that function is there, e to the x function. E to the x function does not change at what? Because remember, the derivative of this function is the function times its derivative at 0.01. It's what call this not its derivative times its gradient at 0.01. So the e function has the gradient at 0.01 being 1, therefore it stays the derivative and the function are actually equal. Very unique, very useful, very important to us. Now we then say, okay, but how do we keep doing this? How do we keep finding out what the derivative of other functions is as 0, 1? It's tedious work, it's a lot of work, it's overwhelming. So we say, let's try and think of a detour, and we'll call it implicit functions. Therefore, implicit derivation. What do we mean here? Let's take y plus xy plus y squared is equal to minus 1. That's our function. Oh God, we are used to dy dx and y was always the subject of the formula. Suddenly it's so tough to make y a solitary subject here. So what do? We say, not problems, solutions. What's the solution in this time? We say, obviously the derivative of the one side, the left hand side, must be the same as the derivative of the right hand side. If the two were equal, yes, then obviously the derivative of the one side must be the derivative of the other side. Now, what do we say? We say the derivative of that as a function in y must, remember, it's implied here that y is equal to f of x. If y is equal to f of x, it's implied. Therefore, that's why we call implicit differentiation here. Now, what it means, therefore, is if this is f of x, derivative of f of x plus x times f of x plus f of x squared is equal to, okay, close that first, is equal to 0, because the derivative of any constant, positive or negative, is going to be 0. Excuse me right there. Now, when we look at the derivative of a sum of functions, we know that it is the derivative of the individual functions. So this we've done before. So we know it's the derivative of that plus the derivative of this product plus the derivative of that function of a function. But we already know the derivative of the right hand side is 0. So now what do we do? Derivative of f of x, but this is y, this is the same as dy. Oh, getting carried away. Dy dx. That's the derivative of y, dy dx. F prime x, dy dx means same thing. Plus. But this is a product here, so we can say the one times the derivative of the other, which is dy dx. If derivative of f of x was dy dx, derivative of that f of x will still be dy dx. So that times the derivative of the other plus, this is one derivative of this center part, plus, I want to look like it's dividing, plus the other, which is f of x, times derivative of the first one. This is go back and do our derivative of products. We've done it before, and I'm sure you are happy with it. So we come and you say, but this is a function of a function. This is a function of a function. So what do? We say inner derivative. So derivative of that is f prime x times the outer derivative is 2 by f of x. This is 2 by f of x, 2 to the minus 1. 2 minus 1, sorry, is going to be 1. So that is the ultimate derivative. This here is the ultimate derivative of a function raised to an order. You get the inner derivative, and then you do the order as if it was just a normal function. X to the power of n. So you would say n x to the power of n minus 1, but in this case it's a function, but then you get the inner derivative. That's how you've done this. So I hope people can just revisit those sections to understand what we're doing here. So this is this derivative here, right there. So this is this third derivative, and it's still equal to 0. Now, but when you interpret, what does this mean here? This is dy dx plus x dy dx plus, but f of x is the same as y plus, this is what? Dy dx by 2 by f of x is y. So this is 2y dy dx is equal to 0. Now, writing it neatly, that would mean let's just go ahead and make what we call this dy dx a common factor for the one section, dy dx, and take all terms that have dy dx 1 plus x, this part, plus 2y, that part. We are only left with what? Because remember, dy dx, that leaves us 1, dy dx leaves us x, dy dx leaves us 2y, plus y is equal to 0. We have done nothing wrong, we are still happy, and then I don't know if people should feel offended right now. But then now, what does this tell you? If you look at that section there, the differential with respect to y was 1. The differential with respect to y was x. The differential with respect to y was 2y. What does this suggest? So our differentials here have simply been, let's suppose I have a function. Therefore, if I have a function, that is a function I want to differentiate g of y, where y is also a function in x. If I want to differentiate this function here, let me rather do this. If I want to differentiate with respect to x a function, this is a function of another function, but in this other function is, this function here g is a function in y, not the traditional system where we've seen our function was what? Was a function in x. We'll say differentiate as if is with respect to y, and then differentiate the y function the normal way. So what I want to people to understand here, what I've done here, if you look at this here, this is a function in y, but I'm differentiating with respect to x. So what do? I say, oh, with respect to y, that's y, but it's times dy dx. That's how I got that part. That one, differential of that with respect to y would be 1. 1 times dy dx would give me dy dx. That one there, if I differentiate this, is going to be x dy dx. If I follow this, the differential of, if I differentiate this, is going to be 1, but that 1 times x, I'm saying this there is going to be 1 dy dx times x, which gives me that part, and then I'm going to have what? I'm going to have y, because the product, I'm going to differentiate dx, which is going to give us 1, hence we get y. Then if I differentiate that with respect to what? To y, that will be 2y, I get 2y there. Then I differentiate, I get dy dx, and I've got that section there. So conclusion, this is how we would do implicit differentiation. We don't forget our product rule when it's products. We don't forget our quotient rule when it's quotients, but we still have to remember, if I'm differentiating the y, I will still differentiate as if it's related to y, and then I will still have to have my dy dx with it. The reason is, it's been proven right there. Now I'm going to go on and say, why have I been doing this? Implicit differentiation is going to lead us to the next and final section. I know sometimes you get carried away and you forget what you need, what you want to say, and you say it wrongly. I've said before that this was going to be our last session. Unfortunately, we have one last section where we combine implicit differentiation with our previous work. And what was our previous work? it was logarithmic differentiation. That being said, let's meet for the next session, and I hope you had fun, because I did have my fun. Thank you. Give us another vote of confidence by heading right back. Ciao, ciao.